Well, we're going to look at the Doppler effect. And the Doppler effect, we've all experienced it at one time or another, but it's the apparent change in frequency. And again, frequency is at lowercase f due to the motion of the source or receiver. If you ever watch NASCAR, here's one of my favorite drivers, old Jeff Gordon, number 24. When they're sitting at the line, they have, what they're doing is they're putting out sound, but there's no movement by the car or you. These sound waves are all moving at a certain speed, and they're neither bunching up or falling behind. They're just being emitted. Neither you or the car is moving. And so when this happens, you really don't hear anything too different. Now, the neat thing is at a NASCAR race, as they start going around the track at 180 miles an hour or whatever, and you're standing there, all of a sudden you hear an increase in frequency, and then as the car goes by you, you hear a decrease in frequency. Well, what ends up happening here, and let me get some of these out of the way here, some of these waves, sound waves out of here. It's really kind of neat what ends up happening. And you hear this quite often, oh, as a train is approaching you or an ambulance is approaching you, you hear this sudden change in frequency. And for sound, that sudden change is called pitch. You know, you hear a higher pitch, and then when it gets by you, you hear a lower pitch. Well, really what ends up happening, and it's not as quite as complex as you think it might be. What ends up happening is, as Jeff Gordon's racing around at 200 miles an hour or whatever, he's actually catching up to his own sound wave. So these sound waves in front of him are starting to get closer together, and as they go behind him, they get farther apart. Farther apart. So, you being the ever faithful viewer of NASCAR, if you are standing here or sitting in your seats, as this car approaches you, the frequency or the pitch goes up. You get that higher pitch, and then as it goes by you, so this would be the high frequency. And again, my frequency fluctuations probably aren't that good. As it goes by you, the waves are spread farther apart, and so you have a low frequency. And again, if you remember, frequency is the number of crests that pass a given point per second, or the number of cycles, and that's measured in hertz. So as he's actually bunching up or getting next to his own, or crunching up or compressing his own sound wave, it's a higher frequency. Behind, he's actually running away from his own sound wave, and so they're spread out and you have a lower frequency. Now, probably one of the best examples of this, let's see if I can get this one here, is this is a F-22 Raptor. One of the best examples of this whole idea of catching up to your own sound waves is a sonic boom. Oops, let's see here. It's a sonic boom. Let's see. Oh, we gotta go 3. It has a sonic boom. In a sonic boom, really, you're catching your sound wave and you're breaking through it. Now remember, we talked about if the plane was standing still, let's say it was on the tarmac, you'd have all these waves going out equally in all directions. Well, on a sonic boom, what you really have is a jet fighter, in this particular case, catching up to. He's compressing his wave here. He's outrunning it behind him. But as he's compressing it, he's actually going faster than the sound he is producing. So sonic boom, or breaking, you hear breaking the sound barrier. Breaking the sound barrier. Whoops. Barrier. The jet is actually outrunning its own sound wave. It's going faster. And if you hit, once you break the sound barrier, that's called Mach 1, or 1 time the speed of sound. I don't know if I have time to get into it, but the speed of sound really depends upon the temperature of the atmosphere. So that's why they don't give Mach 1 a definite number. They call it Mach 1 if you go twice the speed of sound. Mach 2. An F-22 Raptor, I'm sure it's probably classified, but it probably can get to Mach 3 or whatever. So that's what's happening here. Another visualization of this, if you've got a boat, if you got some water skiers here, it's one lousy boat, but what happens is you start to see the bow waves come off, and you always got the skiers. I know I've been paddle boarding and these boats come by, and what happens is they throw some waves out there. It's another good visualization of that. The waves are all bunched up close, but then they kind of start spreading out as the boat moves away from its own waves. So that is the how a sonic boom takes place. One other thing, this can also happen with light. And we'll talk about this a little bit more when we get into the astronomy. But the Doppler effect, you've got two possibilities. You've got a redshift. Well, actually, maybe we can put the color in there for a redshift. We can do that. You got a redshift. And the same thing can happen with light. In a redshift, and we looked at the electromagnetic spectrum, and you look at light and the electromagnetic spectrum. Red, it goes from red to violet or blue. This is low frequency of light, and this is high frequency of light. Well, the redshift is evidence for an expanding universe. Expanding universe. What this is actually saying is the universe is expanding because as we're sitting here on Earth and the stars produce light, that these stars are actually outrunning their own light wave. Now, it's not a lot, so don't think, wow, these things, it's fast, granted, but they're moving away. So as we view the stars, or the star's light, the frequency of this light is shifted towards the red side, or the low frequency side of the light spectrum. So redshift, expanding universe. Now, if the universe was contracting, it would be called the blue shift. Contracting universe. Or stars are coming towards, well, actually the star's light, it's coming towards the Earth. So if we've got the Earth, let's say we got the Earth here, and we've got some star way out there, and we got a star out here, and it's moving away, it's going to be shifted to the red side. So this is a red shift. Now we're going to get into the Big Bang Theory a little bit later, but this is really what it's trying to tell us. The blue shift, on the other hand, let's say if we've got a star out here, the light would be coming or catching up or condensing or compressing its own light wave, and that would be called a blue shift. And this all has to deal with this whole idea of the Doppler effect. You're either catching up to your own wave or you're running away from it. So it takes care of this unit. We'll come back to this a little bit when we talk about the Big Bang Theory and some evidence for it. So we'll catch you a little bit later.